first order um, linear differential equation, or sometimes we just call it solving first ordinary differential equation by using product rules and integrating factor methods. All right, how is that possible? Let's explore this. Right? Now, first, just to recap on how to apply product rules to these methods of solving first ordinary differential equation. Okay, now I'm going to rewrite this problem here. We are given x over y dy dx. Now, at first glance, it may not be that obvious, but after a few restructuring, for instance, if I restructure in such a way, it will look something like this. Okay, now I'm going to rewrite this as x, because here I recognize that the y is indirectly attached to the dy dx. So it's a bit of your exposure to your past knowledge. And then this is typically look like a 1 multiplied with ln y equal to x plus 1. Okay, now this one here is quite significant in this case, because we know that I'm going to show you step by step how all this would appear as a product rule. Would have a relationship to a product rule here. Now, one can be indicated as the differentiation of x. No, hold on. I think it's better to write the other way around. Okay. So the 1 is basically the differentiation of x. All right. So that's how it look like at this point of time. And then furthermore, we also recognize that 1 over y dy dx is indirectly a differentiations of natural log y. So that is typically d dx. I would say there is an implicit differentiations of natural log y in this case. Okay, and then from here you will straight away recognize that it has something to do with the product rule, where this term is a u, whereby this term is a v, and then this part here will be dv dx, whereby this term is du dx. So as a reminder, I'm going to write down at the side here. We know that the differentiation of product of function of x in this case is given as u dv dx plus v du dx. So what we have here is the left hand side expression is indicated by this expression here. So I hope that is clear. From here, the whole expression on the left hand side can be represented as the expression on the left hand side here. So this whole thing can be expressed as d dx, because we have identified the u as x, and then whereby the v as ln y. Therefore, we can express this or simplify this as x ln y. And then that would be the same as x plus 1. And then with a little bit of restructuring, we can actually write this as dx ln y equal to x plus dx here. And then of course we are interested to obtain the solution. By getting the solutions, we mean applying integration. So antiderivative here, we're going to apply antiderivative both sides. Here is a 1, just in case you're not sure what you're looking at. Now, therefore, by solving these integrations, that would actually yield, I will write it down somewhere here, it's easier to see here. Okay, so that solutions to these integrations will be x ln y equal to a half x squared plus a x plus a c here, where I will make an assertion here where the c are all real numbers, just for reference. Now that will be our what we call as the general solutions, right? So this is the general solutions to our first order ordinary differential equations. All right. Now I hope that has been clear. A revisit of differentiating using product rules, and then how that knowledge will help us to integrate or apply integrations to solve for this first order differential equation. All right, so that is the first part. Now, is there another way to solve this using a more systematic method? Yes, of course. So the second part, I'm going to show it to you in a short while, how to apply integration using integrating factor. Now we're going to solve this with a different approach, solving this using integrating factor method. Right? So now before we can solve this using integrating factor, we have to rearrange these expressions. So the first step, I'm going to rearrange it in such a way so that we can have something like this. Y, okay, hold on. Just let me rewrite that properly. So there should be a y, 1 over x here, ln y, look at y here. Right. So I can rearrange this so that I have this structure by dividing both sides by x over y, or multiplying them by y over x. So by doing so, I will be able to get y over x, x plus 1 here. Okay, so I hope that is clear. This is how we are going to restructure it first, so that the coefficient of dy dx is always a 1. So whenever we apply integrating factor, we have to make sure, from my perspective, we have to make sure the coefficient of dy dx should always be equal to 1. So that it's easier for us to mix and match into the integrating factor form. Now, the challenging section here would be this part. Usually by using integrating factor, this expression here should be a function of x. But here we found that it consists of a mixture of a function of x and y combining together. So it's pretty hard for us to apply the integrating factor directly. But don't worry, we can modify it a bit with a bit of algebraic manipulations and differentiations. We're going to see how we're going to do that. Now before that, I might, okay. So before that, we're going to consider this expression first before we are going to apply the integrating factor. So we're going to consider, sorry, not consider here, I would say we are going to let z, let another variable z equal to ln y over x here. So we're going to consider this as a z. And then we're going to apply a bit of differentiation here just to see whether it is helpful to us. So we're going to differentiate this with respect to x. Now, you can either apply a product rule in this case. For me, I would rather apply a product rule. So that will be, let me see, that will be 1 over xy dy dx. We're going to differentiate that implicitly, of course. Or secondly, we will have, if we differentiate this, that will be a negative. Okay, hold on. So let me clean this up. that will be a negative 1 over x squared ln y. So that's how the differentiation of z with respect to x would look like at this point. Right? And then we're going to check this expression with the original expression that we have. Our intention is to obtain the term dy dx here. Right? So we do have dy dx here. By restructuring, we will have, I'm going to do it slowly. So dy dx is equal to, so in this case, I would say that is 1, not 1, sorry. That will be a dz dx plus 1 over x squared ln y. And then, of course, I'm only interested to get dy dx. Therefore, my dy dx should be the same as xy dz dx plus, in this case, I will have the x cancel off, so I still have y over x ln y. Okay, now this expression here is very important at this point. Right. So I'm going to substitute my equation number 2 into equations number 1 here. So what I'm going to get at this point will be, I will have xy dz dx plus y x ln y, and then this part here is also another y x ln y if you want to keep it as it is. Okay, so that's how it looked like. Okay. And then from here you will notice that all the y indirectly can be cancelled. So all the y can be cancelled. So in this case, I will just write down as y, so x dz dx plus these two the same term. So it's basically just 2 1 over x ln y. So that will be 1 over x. You can simplify that by having 1 plus 1 over x. That's how it looked like. And then furthermore, we know that we recognize that 1 over x ln y, we have actually represented as a z. So why don't we just change this to z instead? So that will be dz dx plus 2z equal to 1 plus 1 over x. Now that's what we have currently. And then we still need to convert this into a form that looks something like this, where the coefficient of the dz dx or coefficient of dy dx must be held at 1. Right? So we get to restructure this. Therefore, we get dz dx must be the same as 2 over x z equal to 1 over x plus 1 over x squared. Okay, now you can see that this is the form that we can use to work with integrating function. That's right, integrating factor method. So I'm going to work out this. So we're going to consider this now. Now, integrating factor. By using integrating factor, so I'm going to write down the title here, integrating factor. So integrating factor, we are going to find out the integrating factor function in this case, which is given by exponential integrations of the functions 2 over x here, in this case. Right. Now, by simplifying this, you should be able to obtain this quite easily. I'll just rewrite this as this is basically ln x squared, which is an x squared. So that will be our I. And then by using this technique, we can express this whole term in this case here. So I'm going to rewrite this one more time at the top here. So I'm going to erase off all this, and then I'm going to show you how it looks like. So I'm going to take the important section here. The top part will still be our main objective. Okay. I'm going to keep the last term there because we're going to refer that back shortly. So knowing that the integrating factor is this, we're going to multiply this integrating factor to the left and right of this expression. So for this expression here, we're going to multiply dz dx plus 2 over x I z is equal to I, which is the integrating factor, 1 over x squared. Alright, now that's how it looked like at this point of time. Now, of course, I'm going to put in this x2 here. There will be x2 dz dx, and then there will be a 2x x2 z equal to x2 1 over x plus 1 over x squared. Now at this point we can simplify this, which is actually x plus a 1. Okay, and then here we can also do a bit of simplification if you want. In this case, this is basically 2x z equal to x plus 1. Now you will notice straight away this involves product rule, where this section here is a u, and then this section here, this section, I wrote down the wrong section here, where this section is a u, and then the other section is a v in this case. Right? This part here will be our du dx, because if I differentiate this, I will get 2x, whereby this part here will be my dv dx, if you recognize it correctly. Now therefore, because we recognize the form of product rules, so we can express this whole term as d dx, basically u, which is x squared, and a z, the same as x plus 1. Alright, now I hope that is clear at this point. And then of course the last part will not be that tough. All we need to do is we're going to write this. That will be the integrations of this. That will be half x squared plus x, plus x in this case. And then now finally, of course, finally in this case, we don't forget we have a c, plus a c. But don't forget, what is a z? Yeah, I forgot. I indirectly erased off that, but I'm going to rewrite again. Take note, the z in this case is, I'm not supposed to write it down here. It's very crowded. So take note that we have let z equal to ln y over x. So this is the time for us to substitute back into this final expression. So that will be x squared ln y over x equal to half x squared plus x plus a c. And then finally, if you simplify that, you will get half x squared plus x plus a c. Now that will be exactly the same result that we have obtained from the previous methods of just applying the product rule. Right? This is the most systematic method, but yet it takes a very long turn, and then it involves us to use this integrating factor here. But anyway, it's a very systematic method. There is a pro and con to this. For this example, it will be a bit of con because it takes a while to work out the same solutions where we can actually obtain it directly from the product rule. Right? Now I hope that is clear up to this point. Alright, thank you very much for watching this. There will be more videos uploaded in the future. So don't forget to subscribe and then press the notifications bell. Thank you very much.